So this going on page 54 and we're done. We are stepping our way closer and closer to actually graphing rational functions, right? Getting all the tools in our tool belts that we need. So one of the things that we're going to talk about today are the discontinuities that we are going to face in rational functions. So if you remember with polynomials, they're continuous. From negative infinity to infinity, they're continuous. You never have to pick up your pencil. But with rationals, it says here, most rational functions, which implies not all, right? Most rational functions have restricted domains leading to discontinuities. So a restricted domain means it's not all real numbers. It's restricted somehow. I have to go from negative infinity to 0 and then 0 to infinity because I have a vertical asymptote there, something like that. So not all rational functions, and we will look at least one next week sometime that doesn't have a restricted domain, but most of the ones that we're going to encounter have discontinuities. The types of discontinuities we can have: vertical asymptotes, which we've already talked about; horizontal asymptotes, which we've already talked about, right? Middle behavior, end behavior; slant asymptotes, which are from Algebra 2; and point discontinuities, which are from Algebra 2, how you find them. But we've also already talked about them when we talked about discontinuities when we were just writing domains and stuff, okay? So none of this should be brand new, but we're going to take it kind of to a different level and look at some things that you didn't necessarily look at when you did these. So let's talk about asymptotes first. So this is a picture of a graph that's very similar to one I think that was on our notes yesterday, where we have two vertical asymptotes and we have a horizontal asymptote. And I showed you this one, well, it was on the notes, but we talked about the fact that you may have either been taught, or sometimes it's not necessarily what the teacher said, but it was the impression that you got because of all the examples that you saw. Like maybe your teacher didn't say, you can never ever cross an asymptote. Maybe that's not the way they stated it, but that's the way like your brain registered it because that's every asymptote you saw you didn't cross. So either way. A horizontal asymptote deals with end behavior. So at the end over here, the function is approaching it from the top. Over here, it's approaching it from the bottom. This part of the function crosses the horizontal asymptote. Totally fine. That's middle behavior, so we don't really care anyway. Vertical asymptotes you will never cross because that does affect a domain. It's there because there is not a y value that exists that you could make this happen. So if I cross it, that means I do have a y value. So you will never intersect a vertical asymptote. But you can have an infinite amount of vertical asymptotes. You can also have multiple horizontal asymptotes. There's only one function we'll look at next semester that we're going to look at two horizontal asymptotes. The rest kind of comes a little bit later in math, so we're going to stick with one horizontal. But having multiple vertical ones is not going to be that big a deal. So here's an example. Here's another example of a function that crosses it, and doesn't have just like a middle funky piece. Not all functions that you will see graphed necessarily have the asymptotes graphed for you. Anytime you graph them, you should graph them. I mean, unless it's on Delta Math, it doesn't let you. But if you're graphing it by hand, you need to put dotted lines in there. That helps you graph it hugely, trust me. So there actually is an asymptote here at y equals 0. And so you can see that on both ends, if we're talking about end behavior, the function on both sides is approaching 0. Here comes down and it approaches 0 from the top. Here, bless you, comes down, it crosses the asymptote, bless you, but then it comes back up and it approaches it from underneath. Okay? So, and again, we could cross it once, we could cross it an infinite amount of times. Let's look at that. Here's a function that crosses the asymptote an infinite amount of times. Your asymptote is y equals 0. This is an oscillating function. We'll kind of look at some of these next semester as well. But and it gets closer and closer to 0 as it gets really, really far down at the ends. So it's not like you're only allowed to intersect it once. It could be an infinite amount of times, of course, depending on the function itself. All right, so the other thing we have are slant asymptotes. Here's a function that has a vertical asymptote and a slant asymptote, and it's slanty, hence the name slant asymptote, right? Just like you still never cross a vertical asymptote, but the slant asymptote deals with end behavior because as x gets smaller and smaller and smaller, so as x approaches negative infinity, the function is approaching whatever the value of this line is, okay? And same thing out here, it's still end behavior. So we could cross a slant asymptote, not a vertical. So let me show you a couple of examples of this. This one's kind of hard to see. I tried to replicate it, but it looked terrible, so I figured I could talk you through this one a little bit better. But there is a vertical asymptote here that's not graphed. I have a slant asymptote. That part of the graph doesn't intersect it at all. This part of the graph, it comes up, and then it crosses it, it comes back down, and it actually, the red's underneath the blue, you can just barely see it, because it just gets really, really close to that line, okay? Here's one where it's a little easier to see. We have a vertical asymptote. Here's our slant asymptote. It crosses it, and then it hugs it from underneath. Okay? And I think I just have one more to show you. But not all asymptotes have to be lines. Now, we're only going to deal with asymptotes that are lines, but I want you to know that things are out there. Kind of like when you first started solving systems of equations. Everything you did was lines. Everything you graphed was lines, and you found where the lines intersected, right? So that is a process that works for any function. It could be where two parabolas intersect. The work's just going to look different, and the graph looks different, but it's still the same way. So an asymptote could be a parabola. So the blue part of this function is the function itself, this right here. And this is just a cubic divided by a linear, so it doesn't even look that crazy compared to other things that we've seen. But you get what that blue graph is. The red part of this, that is actually your asymptote. So this asymptote is a parabola. We could have an asymptote that is a cubic. Again, we are not going to deal with that in this class. I just want you to know that there are other things out there and want you to know that asymptotes don't always have to be lines. For the sake of this class, they will always be lines, but just moving forward. Okay, we good with that? Okay, and we're going to come back and revisit this one in just a minute as we get through something else. All right, oops. So let's talk about our discontinuities. So point discontinuities, again, that's something that you did in Algebra 2. You found them at least. We've talked about the fact that you can have a hole in the graph and did some domain stuff, but now we're going to remind ourselves on how to find it. So when we abbreviate it, we'll abbreviate it PD. That's point discontinuity. Another word for point discontinuity is removable discontinuity, and then it is a hole. So yes, it's a hole, but the name of what makes the hole is a point discontinuity or removable discontinuity. So it does give us a hole in the graph. So that occurs when a factor containing x, it's got to contain x, is common to the numerator and denominator. Right? And the holes are one of the first things that you look for when we're looking for all the pieces we need to put the puzzle of rationals together. So the first thing you always want to do with your rational is factor it. Okay? So I'm going to start off by factoring this. Now my denominator, okay, so even though you don't have to write the numerator this way, I could leave it as x squared. But just for the sake of this, I'm going to write it as x times x. It's still considered factored if you leave it as x squared, just doing it for this one. The denominator, I can factor out a 3x. That leaves me with x minus 2. So this says it occurs when a factor containing x is common to the numerator and denominator. So here's a factor that contains x, and here's a factor, and it's common to the numerator and denominator, right? It's not just that there's an x in there, because this x right here is not a factor. So when I find that, I can reduce this fraction, and when I reduce it, whatever it is that was common to the numerator and denominator, whatever that factor was, you set it equal to 0 and solve. Well, that's just x equals 0. There's nothing really exciting right there. That gives you the x value of your whole. Right? So my point discontinuity, since it is a point, my answer is going to be an ordered pair. My x value comes from whatever I cancel out, and I set it equal to 0, so this is 0. So then I have a reduced function. So now I say that f of x is equal to x over x minus 2, because that's what's left. Make sense? I canceled out that x. Oh, wait, I lost something. I lost the 3. Oh, no. Shoot, caught myself there. You know what? I have a really bad feeling I didn't put the 3 there last period. Nobody said anything. But I could be wrong about that. All right, so that's what I actually have. All right, so now that I have that, that's my reduced function. I need to take this number, this x value, and I'm going to substitute it in here. So I'm going to find f of 0. That is equal to 0 over 3 times 0 minus 2. Well, what is 0 divided by anything? 0. Okay, so this is equal to 0, which means the y value here is 0. Okay, so my point my whole is at 0, 0. So this is what I end up with. I have this and this. These are the two pieces, and here's what happens here. My graph looks like this. Looks like this. Okay, that's the thing that we would actually graph with a hole here. So we reduce our function, but when we reduce it, we can't just ignore what we canceled out. That gives us a point discontinuity, so we take care of that, and then our reduced function is what we actually graph. We use for the rest of this stuff. Okay, we good on that? What questions you got? All right, then let's look at number 2. I'm going to start by factoring. So the numerator is going to give me x minus 3 and x plus 2. My denominator is going to give me x plus 3 times x minus 3. So I can reduce this, correct? I can cancel these out. So that means I get x minus 3 equals 0, so x equals 3. So that means for my whole, which is my point discontinuity, my x value is 3. We'll figure out the y value in just a second. My reduced function, f of x, is equal to x plus 2 over x plus 3. So reduced function, what I would actually use to graph, I also need to use this to find this point discontinuity. So this 3 goes in right there. So I do f of 3. That's equal to 3 plus 2 over 3 plus 3. That is 5 over 6. So my point discontinuity is 3, 5/6. That's where the whole is. Okay. What questions you got? We good? Okay. All right, so 3. Let's factor 3. In the numerator, I can factor out a 2x. That leaves me with x minus 3 over 2x. So I can cancel out that 2x, and I say 2x equals 0, which means x has to equal 0. So my point discontinuity over here has a 0 for the x value. My reduced function, f of x, is equal to x minus 3. If I was to graph that, what is that graph? What does it look like? A line, right? Y equals x minus 3 is just a line. So this is how you get a line with a hole in it. So we know how to graph this line. Now we got to figure out where the hole is. So I do f of 0, and that's equal to 0 minus 3, which is negative 3. So the hole is at 0, negative 3. So if you're wondering how you get a line with a hole in it, it starts off looking like it's a rational function, but then things cancel out, and that's where the hole comes from. Okay. What questions you got? Okay. So now let's talk about vertical asymptotes, which we've already talked about together, but we're going to add a little something to this. So vertical asymptotes, they occur when a factor containing x is unique to the denominator. So the way we've looked at them so far, just because I knew what was going to happen with these questions, is we just took what was in the denominator and found our vertical asymptotes with that. But we have to make sure that it is unique to the denominator. So the first thing you do on all of these is factor, if you can. I can't factor this one, right? There's nothing's going to factor. Can I cancel the x's? No. If you think so, get out. No. All right, so can I cancel the x's? So I can't do anything. So I just take the denominator, just like we've been doing the other day, and I say x plus 2 equals 0. So x equals negative 2. So my vertical asymptote is x equals negative 2, right? Not just negative 2. It is an equation of a line. An equation requires an equal sign. Okay? Easy enough. But like I said, we've really already done that together. All right, so let's look at number 2. Looks like maybe I have an asymptote at x equals 7. Let's see what happens here. So I'm going to factor, and I'm going to get x plus 7 times x minus 7 all over x minus 7. Good Lord. Okay. So can I simplify this? Yes. I have a factor containing x in the denominator. Is it unique to the denominator? No. If it was unique to the denominator, it wouldn't also be in the numerator, which it is. So this is going to cancel out, and then what happened? What is that giving me? Okay, no, okay. Yes, you're right. Let me re-ask the question differently. The parts that I'm canceling out, what does that part give me? A whole. Yeah, that's what I was going for. You were right, but bad question. So that means still, I'm not going to ignore the fact that I have a whole, so that means that x minus 7 equals 0, so I get x equals 7. I know this is only asking, well, actually it doesn't even ask a question, so we're really only looking at vertical asymptotes here, but we're going to go ahead, if we come up with a whole, we're going to take care of this. So I am going to have a point discontinuity also, because this has to come first. And my x value is 7. My reduced function is f of x equals x plus 7. So in order for me to find my point discontinuity, I have to find f of 7. That's equal to 7 plus 7. So this is 14. Okay. Everybody okay with that? With my reduced function, do I have a factor containing x that's unique to the denominator? No. If I don't even have a denominator. If I wanted to force this into a fraction, my denominator is 1, right? So I don't have any vertical asymptotes. None. Don't always necessarily have them. Once again, this is a line with a hole in it. Okay? Questions? All right. So let's look at number 3. We're going to factor. So we get 2 times x minus 4. In the denominator, I get x plus 4 times x minus 4. Okay. I do not have 2 vertical asymptotes because this is unique to the denominator. This is not. This is going to cancel with the numerator. So I have x minus 4 equals 0, so x equals 4. So that means I have point discontinuity with an x value of 4. My reduced function is 2 over x plus 4. I have to find f of 4 because it comes from here. That's going to be equal to 2 over 4 plus 4, which is 2 over 8, which is 1/4. So I have a whole at 4 1/4. Okay? That has to come first. Then I can take this denominator and say, all right, now I have x plus 4 equals 0, so x equals negative 4, and my vertical asymptote is that x equals negative 4. Look at the 2 different ways I use this information. I set this equal to 0 and I got x equals 4. But I didn't come over here and write x equals 4. I put it in for 4 where x goes in the hole because I'm using this based on what it is it's trying to tell me. Here I got x equals negative 4, and that's what I wrote right here because that's an equation of a line. So make sure you know how to use what you're getting because they look the same. I mean, it looks like they say x equals 4, x equals negative 4. What does it mean? It means that I have a hole with an x value of 4. It means that I have a vertical asymptote at x equals negative 4. So you got to know how to interpret what you're getting there. Okay? All right. On number 4, it's already factored for me. That's nice. Can I reduce anything? No. Right? Which means I have how many vertical asymptotes? 2. So I set this one equal to 0 and this one equal to 0. So I get x equals 0 and I get x plus 5 equals 0. So x equals negative 5. So my answer over here then is that I have a vertical asymptote at x equals 0 and x equals negative 5. I do not write it in the little squiggly brackets as a set because that makes no sense because these are equations of lines. Okay. What questions you got? Okay. Double check I said something up here. Okay, I did. All righty. So now we're going to look at horizontal asymptotes, okay, which I know you went through at least these 2 things. Well, at least this probably. I think you would have talked about all of them in Algebra 2. You would have had to. Whether or not we use them all the time, that's a different story. But So horizontal asymptotes, they require little to no work to figure out. You just have to understand what's happening in your function. You also don't have to factor for it, so that's good too. So this occurs when the degree of the denominator is greater than or equal to the degree of the numerator in a rational function. Okay, that's when you get a horizontal asymptote. Three things could happen as far as degrees are concerned. Your function could be top heavy, bottom heavy, or tied in degree. And when we're talking about the top heavy, bottom heavy, we're looking at the degree of the leading coefficient of the numerator and denominator. So when I look here at 2x squared and x, I don't care about the rest of it. X squared is a higher degree than x. Do we agree with that? That's what makes it top heavy. Top heavy is greater degree in the numerator. That indicates no horizontal asymptote. So if you look at this and you say, that's top heavy, then your horizontal asymptote answer is none. When you look here, we look at x cubed and x squared. That's top heavy again, so that means for horizontal asymptote, you have none. Now, I still could have here clearly, I still have, well, I say clearly because we didn't factor, but I could possibly still have a vertical asymptote. That's totally possible. And if you do not have a horizontal asymptote, that opens the door for you to have a slant asymptote. Doesn't guarantee a slant asymptote. We'll talk a little bit more about that. But if you look at it and it's like none, then you check for slant. Okay? Questions about that? All right, so let's look at bottom heavy. So bottom heavy in degree, greater degree in the denominator indicates horizontal asymptote at y equals 0. So when you look at this one, you got 2x to the first in the denominator. There's not even an x in the numerator. Clearly that's bottom heavy. So your horizontal asymptote is at y equals 0. Okay. When we look at 4, you look at 2x and you look at x squared. The degree is larger in the denominator, makes it top heavy. So your horizontal asymptote, y equals 0. Okay. Easy enough? We good? All right. So then we have tied in degree. Right? So tied in degree leads to a horizontal asymptote where y equals the ratio of the leading coefficients. So we look at these, 2x and 5x. Okay? And they're tied in degree because they're both to the first power, right? Caroline, are you with me? So that means that I do have a horizontal asymptote, and that's at y equals, so the ratio of the leading coefficients is 2 over 5, it's just 2/5. So that's the very little work you'd have to do. And then I look at number 6. Here are my leading terms. I am tied in degree once again, so my horizontal asymptote. And again, these are lines, so it has to be y equals, what would this one be? 1. Yeah. So it's 2 over 2, which is 1, because we wouldn't write 2 over 2. What questions you got? We good? Okay. So slant asymptotes, we'll abbreviate SA for slant asymptote. Anybody give me the other name for slant asymptotes? Starts with an O. It's oblique. You can have oblique asymptotes. You can have oblique polygons. You can have oblique polyhedrons. Like if you have a prism and it's leaning over some, it's oblique. You have oblique muscles. Where are your oblique muscles? Where are your obliques? They're right here, right? What do they help you do? Lean over. That's why they're called the obliques, by the way, because it's leaning like the line is and like the figures are. It's all tied together. Here's where we did cross-curricular with PE and math, all right? It's all together. Okay, so slant asymptotes occur when the reduced rational function, which means you better have gotten rid of those holes if you got any, contains an x in the denominator and numerator is greater than and the numerator is 1 greater in degree than the denominator. This 1 greater is important. Okay, so let's go back up here real quick. We said if it's top heavy, we don't have a horizontal asymptote because you're not going to have horizontal and slant at the same time. So if it's top heavy, it's no horizontal asymptote, and opens the door to a slant asymptote. Because it doesn't guarantee a slant. It only is going to have a slant asymptote if the degree of the numerator is 1 greater than the denominator. So this one here, I would have a slant asymptote. This one here, I would also have a slant asymptote. But this 1 greater in degree is important because if we look back here, look what we have here. This is top heavy, right? We have x cubed over x, so this is 2 greater. Since it's 2 greater, my asymptote is not a line, it's a parabola. If it was 3 greater, it would be a cubic, okay? That's how you determine that stuff. So I want you to know that it exists. So if it's more than 1 greater, we're just not even going to find one right now, and you shouldn't really come up against any of those. I've been trying to not make the graphs too terribly crazy. But it has to be only, that's why we look at 1 greater in degree, because we only want it to be a line right now. All right, so the first thing we do on all these is not, hey, I think I have a vertical asymptote. Maybe I do, but I have to factor first. So I'm going to factor, and I'm going to get x minus 3 times x minus 1 over x minus 2. Okay? So there it is factored. Do I have any point discontinuity? No. So that is my reduced function, because it has to be the reduced function. So it says, so I have a slant asymptote because it's only 1 greater, and then it says it is found by dividing the numerator by the denominator. So how do we divide polynomials? What are our options? Have we divided polynomials? It was on your last test. What are our 2 options on how to do it? Long division and synthetic division. Okay. Long division and synthetic division. If I'm going to do long division or synthetic division, I don't want the factored form. So I had to factor it to check to see if I could reduce it at all. And I can't, but this is the form that I need. So if it gives me a factored form, I'm going to have to multiply it back together so I can actually divide. Can I use synthetic division on this one? Yes. So if I can, I'm going to. So what goes outside the little box? 2. And then inside, make sure you don't have any missing factors, which we don't. So it's 1, -4, and 3. Then you should be able to run through this pretty quickly. Bring down the 1. This is 2, -2, -4, -1. Okay, so let's think about what this tells us. We got a remainder. I don't know if you were expecting one or not. But if I didn't get a remainder, that means it divides evenly. So if I don't get a remainder, that means it divides evenly, which means there should have been something I could cancel out, and I missed a hole somewhere, all right? When you are looking for a slant asymptote, you will have a remainder. If you don't, you did something wrong somewhere, okay? So we know, and I'm not going to write this down because I don't want to confuse it, but since there's 2 terms, this is going to be x minus 2, then it'll be plus -1 over x minus 2, right? That's what it gives me. But we're looking for the equation of a line. My slant asymptote, and we don't know how to graph lines that have remainders, right? My slant asymptote, I take from this part, y equals, because it is a line, x minus 2, and we ignore the remainder. We have to have one, but then we ignore it. Tomorrow, I will tell you what the remainder tells us and what it means, but I don't want to do too much today, so just kind of do it just right now. Just know that you ignore it. You're still going to ignore it after tomorrow, but at least make sense why it exists. Okay, we good? So this is it. This is my slant asymptote. All right, so let's look at number 2. Again, we start by factoring. So in the numerator, I have 2x times x minus 2 over 2x. Can I reduce this? Yes. So I'm going to cancel those out, and I'm going to say that means 2x equals 0, so x equals 0. So my point discontinuity has an x value of 0. My reduced function f of x is equal to x minus 2. So that means that the y value is -2 here. That's where I have a hole. Okay. Now I'm looking for a slant asymptote. The definition I gave you says, oh, where am I going? It has to be 1 greater, which it was, and even still, over 1, this would still be 1 greater in degree than the denominator. But it also says it has to contain an x in the denominator. Does this contain an x in the denominator? No, right? It would just be a 1. So my answer here for my slant asymptote is none. We're going to revisit this as well, because you can also look at it as, since it's a line, it's its own slant asymptote. But again, I don't want to make your brain hurt too much now, so we're just going to go with none until we come back and revisit it. So I'm not really lying to you. I'll clean it up, but wait till this all makes a little bit more sense. Okay, let's look at number 3. So I could start, I said we always start off by factoring, but let's think about this. If I factored the numerator, and personally I don't even know if it factors or not, I don't know. I don't really care at this point, but if I were to factor it, I'd have 2 binomials, right? So if I have 2 binomials divided by this, would I be able to reduce anything? No, because I don't have a GCF or anything. So, and what I'm looking for is my slant asymptote, so I'd have to multiply it back together anyway, so there's really no need to factor it. Does that make sense? You can kind of reason through that. All right, so instead, I'm going to have to just go ahead and, I look, first of all, 1 degree greater than the denominator, so I'll have a slant asymptote, and I'm going to have to use long division here. So, 2x. The good news is, most of the time when you have to do the long division, it's not going to be crazy, stupid things. You do want to make sure that you're not missing any factors, though, so you don't make a ridiculous mistake, but they won't be crazy hard ones that you have to do. Okay? So 2x goes into 2x squared, 2x times. So then this gives me, oops, no it doesn't. It goes in x times. Goodness gracious. At least I caught myself, right? I lost my 3. Okay, there we go. 2x squared goes into, oh no. 2x goes into 2x squared x times, thank you. So 2x squared minus 2x squared. Then I change my signs, and I get, those cancel out, and I get negative 2x. Am I doing this right? I have this bad feeling that my brain is not. No, it's right. I made something up, didn't I? Oh, I don't know. I don't know. Yeah. Oh my God. I'm making things up. I told you it wasn't going to be hard. It's going to be hard because I'm making stupid mistakes. I was like, wait. I felt like something was wrong. It's because I'm not really paying attention to what I'm doing. All right. So 2x squared divided by 2x does give me x. All right. So then I multiply those, and I get 2x squared. For whatever reason, I did it again and wrote it right there, and it wouldn't make any sense because it would be x squared anyway. Yikes. Okay. So this is 0, and then I bring down my negative 4x. So 2x goes into negative 4x, and negative 2 times, I think. And then negative 4x, and then I bring down my 3. So I have a remainder, don't care about my remainder, right? So my slant asymptote is a line, and it is y equals x minus 2. Now I want to show you a different way to do this that isn't synthetic division, bless you, or long division. And you can decide whether or not you want to commit it to memory. It's up to you, but it does simplify things a little bit. If I have a denominator that is a monomial, not a binomial, a monomial, then I can think about it this way. And you wouldn't even necessarily have to write this first step I'm writing. I'm just going to write it so I don't lose you. So I can split this up into 2x squared over 2x minus 4x over 2x plus 3 over 2x. Do you agree that that's the same thing? It's like undoing the common denominator, like taking it apart. Okay, so then, since I have it chopped up into those 3 pieces, I can reduce. 2x squared divided by x is x. Negative 4x divided by 2x is negative 2, and then that's my remainder that I don't want, and boom, there's your answer. So I wrote this step so I would, like I said, so I wouldn't lose you, but if you know that it's a monomial, then you can really just reduce, each thing, like you reduce it with this one, you reduce it with this one, and it doesn't reduce with that one because it's the same thing that's happening, and you can skip that step. So if that makes sense to you, and you're not going to make up math on other things, you can go for it. It's fine, but you know yourself well enough whether or not you want to use a trick. Okay, we good? Any questions? All right, Carolina, you with me? All right, so then let's look at number 4. We should start by factoring. Now, I would think that it would be easier to kind of look at the denominator and know if it factors rather than look at the numerator first, either one. But if I look at the denominator, if I want to factor it, I'd need 2 numbers that multiply to give me a negative 1 with different signs, so my only option is positive 1 and negative 1. And then they'd have to combine to give me a positive 2. So is the denominator going to factor? No. So if it doesn't factor, there's no use in factoring the numerator because nothing's going to cancel because it can't factor the denominator. You with me? So we can kind of skip the factoring process there too. And will I have a slant asymptote here? I look at these. It's top heavy, right? And it's top heavy by 1, so I'm good. Is synthetic division going to work here? No. So I need long division. So go ahead and divide that and find your asymptote. So I know my slant asymptote has to be the equation of a line, right? Is it y equals 27x minus 15? No, because that's my remainder, and I ignore it. It is just y equals 2x minus 8. What questions do you have? Anything? All right, so if you do, let me know. If not, go ahead and tape this in and get started on your Delta Math.